Hello everyone. Some of the students were really having doubt on the topic Mohr Circle. So in this tutorial video, I will just quickly go through this Mohr Circle, and I will try my best to make you understand what is the Mohr Circle and how we are going to use in order to calculate the tangential and normal stresses. So before going to this graphical method, I will just quickly go through an analytical method, and I will just cover all those things in 1 or 2 minutes, so that when I will make you understand this Mohr circle, there will be won't any much problems. So let us consider this to be any specimen, and if we are applying the perpendicular, if you are applying these tensile stresses on this specimen, then okay, and if we are having a oblique plane at an angle of theta degree, this is an oblique plane. If we want to find out the normal stresses as well as this is a normal stress, and if we try to find out what is the tangential stress, this one on an oblique plane, then we have the formula like normal stress is equals to sigma cos square theta, and tangential stress is equal to sigma by 2 sine 2 theta. And if we want to find out the maximum value, then it will be maximum when this theta equals to 0, and that maximum value will be equals to sigma. And similarly, for the maximum value of tangential stress, the theta needs to be 45 to 135 degrees, such that the maximum shear stress will be sigma by 2. Similarly, in the other case, when you are having the normal stresses acting in a perpendicular direction, like in this case, so again from the analytical formula, we had the formula like normal stress equals to sigma 1 plus sigma 2 over 2 plus sigma 1 minus sigma 2 over 2 cos 2 theta. And for this tangential stress, we have sigma 1 minus sigma 2 over 2 sine 2 theta. And if we want to just find out the resultant of both of these stresses, then it will be under root of sigma n square plus sigma t square. And if you want to find out that theta, that phi value, then it will be tan phi equals to sigma t over sigma n. And similarly, if we want to find out the maximum value of the shear stress, then that will be at an angle of 45 degree and 135 degree, and its maximum value would be sigma 1 minus sigma 2 over 2. Similarly, for the principal plane, if the angle theta equals to 0 degree, the normal stress will be sigma 1, and if it is equals to 90 degree, the normal stress is going to be sigma 2. And the third case that we have seen was when only these shear forces was acting on this plane. Okay, so when this happens, the normal stress was tau sine 2 theta, and the tangential stress was minus tau cos 2 theta. And when it was a combination of this normal and the shear stresses, then again we had seen the normal and the shear tangential stress formula. Normal was sigma 1 plus sigma 2. Let us suppose that this is sigma 1 and this is sigma 2. Let us only suppose. Okay, then we had the normal stress value sigma 1 plus sigma 2 over 2 plus sigma 1 minus sigma by 2 cos 2 theta plus tau sine 2 theta, and the tangential was sigma 1 minus sigma 2 over 2 sine 2 theta minus tau cos 2 theta. In this case, if you are talking about the principal plane, then if you put a tangential stress tau sigma tau equals to 0. Why? Because on principal plane shear is 0, so when you put equals to 0, you will get tan 2 theta equals to 2 tau over sigma 1 minus sigma 2. From there, you are going to get the two major and minor principal stresses, which is sigma 1 plus sigma 2 over 2 plus under root of sigma 1 minus 2 over 2 whole square plus tau square, and other will be the minor principal stresses, and both of these major and minor will be at an angle of 90 degrees. Similarly, if you are going to calculate the maximum shear stress in this case, then you have to differentiate the tangential stress with respect to 0 and equate with 0. Then you will going to get tan 2 theta equals to sigma 2 minus sigma 1 over 2 tau, and in that case the maximum shear stress will be half under root of sigma 1 minus sigma 2 whole square plus 4 tau square. And again, if you want to find out the plane at which plane this maximum shear stress is going to act, then it is being seen from this formula that both of these plane will be at an angle of 90 degree. And the other method to find out the plane of maximum shear stress is that at first you find out the plane of the principal plane, okay, and let's suppose that if that plane of the principal plane is acting at an angle of theta 1, okay, then the plane of maximum shear will be at an angle of theta 1 plus 45 degree or theta 1 plus 135 degree. Okay, so at an angle of theta 1 plus 45 degree, it lies a plane of the maximum shear stress, and if you are just going to add theta 1 plus 90, then that will be the plane of minor principal plane. Okay, so that was the analytical method that we had seen in our previous video also. So in this I will quickly go through the this Mohr circle, and I will let you understand why this first case, that how you can draw this Mohr circle. So let us consider the first case that that specimen. I will draw that specimen again for you. This is the specimen, and this is subjected to the stresses sigma 1 and sigma 2 on the mutually perpendicular plane. Let us suppose that this is the case, and here this is subjected to sigma 1 and this is subjected to sigma 2. You must remember one thing that I may have elaborated you in the previous video, that this is actually subjected to not sigma 1, this is actually subjected to the force, that is P1. Okay, remember that it is subjected to force. We are actually applying the force, not the stress. So when this force is multiplied by the cross-sectional area, that is stresses was force acting per unit area. Okay, stress force acting per unit area. So when you are going to just divide this force with its cross-sectional area, and we are taking here the cross-sectional area to be unity, so that's why this is actually replaced by this sigma 1. So this is force P1 over the area, so that gets replaced by sigma 1. So actually we are applying the force, but we used to write here sigma 1, and similarly here you used to write sigma 2. So this two things that you must should have the knowledge. Okay, so let us suppose that the angle here, it is given to an angle of theta is there, and this is the plane of and this is the plane of oblique plane, and you have to find the normal and tangential stress over here. So this same thing could be again, just we can obtain the same thing via this Mohr circle method. Okay, so the first step is that we just need to draw a line, that is AB. This is the line AB, that is equals to sigma 1. So this is a sigma 1 stress that we have applied, so this is AP, that is sigma 1. Again, next thing is sigma 2, that is equals to AC. So this is AC, this is equals to sigma 2, that is stress that we had applied here. Okay, these two things are clear. Now BC, so this is BC, so BC will be equals to the diameter of this Mohr circle. Okay, and let us suppose that this O is the center of this circle, and now through O you are just going to draw a line OE such that the angle will be equals to 2 times of the theta, and you have to draw this line OE with respect to OB, and after going through this point you have to draw a perpendicular from this point over this line of CB. I think this thing can you can draw. Now next thing is that from this point E you have to draw this perpendicular, and everything I think is clear. Now next thing is that let O is the center, and through this I think this thing is done. Now from this figure you can see that this is AD. Okay, so from this AD is equals to the normal stress on an oblique plane. This AD is equals to the sigma n. Okay, and this DE is equals to the tangential stress, and this AE is equals to the resultant stress which is acting on an oblique plane. So remember, this AD is equals to normal stress, DE is equals to the tangential stress, and AE is the equivalent stress that is acting on the plane. Okay, now next thing is that about the Mohr circle radius. So we know that this is CB, that is the diameter, its radius will be equal to CO. Okay, now you have to find the radius. So for that, what you can do, that this is sigma 1. Okay, this is sigma 1. Just to subtract this sigma 2 from this sigma 1, then you will be left with this diameter, and when you will divide by 2, you will be having the radius, that is CO or OB. Okay, so this thing you have obtained from here. Now you have to go on and try to determine the AO. So this is AO. Okay, so this AO will be equals to this AC plus this CO. So we know that this AC equals to sigma 2 and this CO is equals to the radius of this circle. Okay, so we know that this is sigma 2, this is equal to the radius of the circle, hence this AO is equals to the sigma 1 plus sigma 2 over 2. Next thing is that we need to just find out this OD. So this is the triangle OED and this is the angle 2 theta. So we know that cos 2 theta will be equals to base over hypotenuse. Okay, this is base over hypotenuse, and then we can find out this OD. Okay, so here the OD will be equals to OE cos 2 theta. We know the value of OE, and just put the value, you will get OD. Now as I have told you that this AD equals to sigma n, and this is equals to AC plus CO plus OD. So you will, when you are going to add all of these three together, then you are going to get the value of AD, which is equals to the normal stress, and which is equal to sigma 1 plus sigma 2 over 2 plus sigma 1 minus sigma 2 over 2 cos 2 theta. And this is the same formula that we had obtained during the analytical method. This is the normal stress, and this ED is the tangential stress, and which is equals to OE sin 2 theta. Again, use this formula of sin 2 theta, that is perpendicular upon hypotenuse. Put the formula and you will get the tangential stress, that is sigma 1 minus sigma 2 over 2 sin 2 theta. And this is again the same formula that we had obtained in the analytical method. And the last one is this resultant stress. And as you know that if you consider this to be the, one second, if you consider this triangle I'm talking about, if you consider this triangle, okay, this is hypotenuse, this is AD, and this is DE. So this is the resultant AE, this is the resultant, and by using the Pythagorean theorem, you know that this AE square is always equals to the summation of AD square plus DE square. So this AE square will be equals to, obviously, AD square plus DE square, hence this AE is equals to under root of AD square plus DE square. Okay, and you know that this AE is resultant stress, hence you can say that this resultant stress equals to sigma n square plus sigma tau sigma t square. And this is the same formula that we had obtained in the analytical method, that resultant stress equals to under root of sigma n square plus sigma t square. And the same thing we have obtained here by using the Pythagorean theorem, that this resultant stress is equals to the under root of this normal stress square plus square of this tangential stress. Okay, so similarly, if you use this formula, then this technique, then you can again draw the same type of Mohr circle for the remaining cases, like when the normal force acting on the plane as well as shear, and more these two cases. So by this way, you just try to understand this Mohr formula, and more propose this formula in order to just make the analytical method simple. And that is again an alternative way by which you can actually determine the normal as well as tangential stress which is acting on any oblique plane. I hope this will make you understand about the Mohr circle. And again, if you have any doubt, query, then you can contact me. Thank you.